Swayam Prabha. Digital India. Educated India.
Welcome to lecture 14 in mechanics of materials. The last lecture we saw the two remaining equations that connects the four concepts, namely the comparability condition and the constellation. We found that for a smooth displacement field to be obtained from a prescribed strain field, the strain field should satisfy certain restrictions called as comparability conditions, because we did not want the surfaces to open up or penetrate each other. So, that condition gave us in general curl of epsilon equal to 0, and for a plane state of strain we got the equation as 2 times d square epsilon xy by dx dy equal to d square epsilon xx by dy square plus d square epsilon yy by dx square. We also said that if the response were to be elastic and if the material were to be isotropic, we got a constellation for small deformations to be given by sigma to be given by lambda equal to trace epsilon identity plus 2 mu epsilon. This equation is called as the Hooke's law or the linearized relationship between stress and linearized strain. Okay. Now, let us understand what this equation means. So, basically what we said was stress is some function of strain, and we got this relationship between stress and strain because we said that the deformation is small, so that higher order terms in the displacement gradient can be ignored. Okay. Now, what this identity matrix mean? This identity matrix means it is 1 0 0 0 1 0 0 0 1. Okay. Now, we began with the assumption that the stress is a function of strain, but I can do the same thing, derive a same constellation where I want to write epsilon the strain as some function of the stress sigma. Okay. In particular, I want to invert this relationship between stress and strain to get this strain as a function of sigma. Okay. To invert this, first I have to take trace of this constellation. From here I find that trace of sigma is given by lambda trace epsilon, which is a scalar, comes out of the trace expression. Trace of identity tensor is 1 plus 1 which is 3 plus 2 mu trace epsilon, right. So, I get a relationship which says that trace of epsilon is trace of sigma by 3 lambda plus 2 mu. Okay. Now, I want to write epsilon in terms of sigma. So, from this equation I get epsilon to be 1 by 2 mu sigma minus lambda by 2 mu trace epsilon identity matrix. Okay. What I have done is I divided this equation by 2 mu and I have taken this lambda trace epsilon to the other side of the equal to sign. Okay. So, I got this expression. Now, I substitute for trace of epsilon from this equation in here, to get the final expression for epsilon as 1 by 2 mu sigma minus lambda by 3 lambda plus 2 mu trace of sigma times identity matrix. Okay. So, the final expression for strain which will carry forward is the following: epsilon to be given by 1 by 2 mu times sigma minus lambda by 3 lambda plus 2 mu trace sigma identity tensor. Okay. This expression will carry forward. Now, we have to devise experiments or we have to devise techniques to find this material parameters lambda and mu, where lambda and mu are called as Lamé constants or Lamé constants. It turns out that it is difficult to find this Lamé constant directly from an experiment. So, we will do a uniaxial experiment first, which is a common experiment that is done on materials to find the metal parameters, and relate this Young's modulus and Poisson's ratio to the Lamé constants, where Young's modulus and Poisson's ratio are parameters that you obtain from a uniaxial experiment. Okay. So, what is this uniaxial experiment? In a uniaxial experiment, you apply a force along the axis of the member alone. Say this is a member, this is a rod, or this is a square cross section bar, and you pull this bar along a particular direction with a force P. You fix this end, so there will be a reaction force P also coming in there. So, this end is fixed, there will be a reaction force P coming in there. So, what happens now when I pull this bar? It is going to shrink and it is going to expand. It is going to shrink in the lateral direction and it is going to expand in the other direction. Okay. Now, let us say this displacement was delta B, this is A and this end is B, and that deflection was delta B. Okay. Now, I have to assume a displacement field to start solving this boundary value problem, right. Okay. So, the displacement field I assume is, a displacement field U, which is, I want this displacement to be delta B at a distance L from the end A. Say the length of the bar initially was L. Okay. Let us assume a coordinate system 2, let us assume this is x, this is y and this is z, then it is getting displaced by amount delta B along the x direction at x equal to L. Okay. And x equal to 0, I know that the x component of the displacement field is 0. Okay. That is, I know that the x component of the displacement at x equal to 0 is 0 and ux component of the displacement at x equal to L is delta B. Okay. So, since I know these two values, I linearly interpolate for the intermediate displacements as to get ux component to be delta B x by L. You see that when x equal to 0, this component is 0, and when x equal to L, this component is delta B, like what we want. Okay. Similarly, let us assume that uy displacement is given by some delta transverse y by the depth along the direction h, delta transverse along y direction, wherein the cross section is, wherein I have some arbitrary cross section with y and z like this, and I am assuming that this distance is h, okay, and I am assuming that this width is going to be b. Okay. So, then I can write the displacement field as E y plus delta z t, z divided by b into E z. Okay. Okay. Now, I assume the displacement field somewhat appropriate to the problem based on the experimental observation that the strain that I measure is not varying along the axis of the beam, axis of the member. Okay. So, that is the displacement field. So, now I have to compute the gradient of displacement field H, which is gradient of u, which you know is dou ux by dou x, dou ux by dou y, dou ux by dou z, dou uy by dou x, dou uy by dou y, dou uy by dou z, dou uz by dou x, dou uz by dou y, dou uz by dou z. Okay. This will evaluate to be delta B by L 0 0 0 delta transverse y by h 0 0 0 delta T Z by B. Okay. Now, I want to find the strain linearized strain is defined as 1 of H plus H transpose. So, I will get essentially it is only a diagonal matrix. So, I will get the same diagonal matrix again, it will be delta B by L 0 0 0 delta T Y by H 0 0 0 delta T Z by B in here. Okay. Now, what is the stress corresponding to this, or I can rewrite this strain as some epsilon xx 0 0 0 epsilon yy 0 0 0 epsilon zz component of the strain. Okay. So, I will rewrite it as this. Now, I want to write the stress matrix. Okay. I know I am applying a force only along the x direction. So, from there I infer the components of the stress in the prescribed xyz coordinate system will be given by P by A 0 0 0 0 0 0 0 0. This is because I am assuming that the variation of stress along the depth of the cross section, the variation of sigma xx, which is the component of stress due to the applied force, is uniform along the depth, it is uniform along the depth and it is uniform along the width of the cross section. It is uniform along the width of the cross section, or it is uniform over the entire cross sectional area, that is the assumption that I am making. It is uniform along the width of the cross section, that is the assumption I am making in here. Okay. Now, I know the stress because I know what force I applied. So, from here I use a constitutive relation that was prescribed here, that we obtained here in terms of stress. I use this constitutive relation to get the strain. From here I get the strain to be, in terms of the stress, I have 1 by 2 mu P by A 0 0 0 0 0 0 0 0 minus lambda by 3 lambda plus 2 mu P by A into 1 0 0 0 1 0 0 0 1, right. Okay. So, I equate both this strain, I equate the strain obtained here to the strain matrix here. You can see only the diagonal terms are non-zero as we obtained from the assumed displacement field. Okay. So, basically now from here I get to know that epsilon xx would be given by P by A into 1 by 2 mu minus lambda by 2 mu 3 lambda plus 2 mu. Okay. So, this on simplification will give me P by A into 1 by 2 mu into 2 times lambda plus mu divided by 3 lambda plus 2 mu, which simplifies to, let me call it as sigma xx stress into lambda plus mu divided by mu times 3 lambda plus 2 mu. Okay. Now, I defined the first moduli, Young's modulus, which is denoted by E for our purposes here, is defined as the ratio of axial stress by the axial strain, that is the axis along which the stress is applied divided by the strain developed along the same axis. which in our case would be sigma xx by epsilon xx, which from the above equation will boil down to mu times 3 lambda plus 2 mu by lambda plus mu, okay, which will boil down to that expression in here. Thus, Young's modulus is given by mu times 3 lambda plus 2 mu by lambda plus mu. Now, if I define Young's modulus as this, then the equation here, then this equation can be written as equal to sigma xx by E, right. This equation becomes sigma xx by E. So, from there I get sigma xx equal to E times epsilon xx, that is a constellation. Okay. So, now how do I find E? I do an experiment, I measure the force that I am applying and I measure the axial strain epsilon xx, and then I plot epsilon xx versus sigma xx. I plot epsilon xx versus sigma xx, the axial stress versus the axial strain, or this is the axial strain and this is the axial stress. Okay. Now, I will get some data points like this. Okay, I will get some data points like that from the experimental data. Okay. So, now how do I find what is this value of E? I have to do a, to find the value of E, I have to do a curve fitting. Okay. Basically, I want to find a relationship between sigma xx and epsilon xx which is linear and which is close to the data point that are prescribed here. Okay. So, I want to find a curve which will pass through these points, something like this, such that the error between the experiment and the predicted equation, predicted sigma xx is the least. Okay. For this we use the least square method to find the error, to find Young's modulus, assuming this relationship, that is, you define an error quantity called delta, which is sigma xx experimental minus E times epsilon xx experimental. This E times experimental will give you the theoretical estimate of the stress. This I want to square and sum for each ith value of the stress and ith value of the strain that I am estimating, okay, for each of the n number of experimental data points that I have. Okay. So, I equal to 1 to n, I define this as the error measure. Okay. Then to find E, I want to minimize this error. So, I say dou delta by dou E has to be equal to 0, which will give me essentially 2 times summation I equal to 1 to n sigma xx exp I minus E times epsilon xx exp I into epsilon xx exp I equal to 0. Okay. From here, this is a linear equation E, I will solve this linear equation to get E as epsilon xx exp I into epsilon sigma xx exp I divided by epsilon xx exp I both n 1 to n I equal to 1 to n. Okay. So, basically I take a product of all the stress quantities that I obtained with the strain corresponding strain quantities and divided by the square of the strain quantities that I obtained to get the Young's modulus value. Okay. Once I get this Young's modulus value, it will pass through the origin, that is a constant that we have. When sigma is 0, the strain has to be 0, that is a constant that we have, and hence we get this expression for the Young's modulus. Now this is basically relating the axial stress to the axial strain. Okay. So let us go back to the equation we had before, which connects epsilon xx, which will tell what epsilon yy and epsilon zz are in terms of the applied stress sigma xx. You will find that both are the same expression, epsilon yy equal to epsilon zz, which is given by the same expression, which is this term alone. Okay. So let us go ahead and do that. You will find that epsilon yy is equal to epsilon zz is equal to minus lambda by 2 mu 3 lambda plus 2 mu into p by a. Okay. In comparison to this, epsilon xx was lambda plus mu divided by 2 mu divided by mu 3 lambda plus 2 mu times p by a. Okay. Now I defined the second parameter that I want to find from the uniaxial experiment, that is called as the Poisson's ratio. Which we will denote by the symbol nu. Some use the symbol mu also for this, okay, but this we have already used for Lamé constant, so we are not following this notation in here. Okay. So this is defined as the negative of transverse strain to the axial strain. Okay. Negative of the transverse strain to the axial strain, which in our notation is nothing but minus epsilon yy by epsilon xx. Okay. Now substituting for epsilon yy and epsilon xx from this equation, you find that this ratio is given by plus lambda by lambda plus mu. Okay. This is a Poisson's ratio. Okay. So you have now the relationship that epsilon xx or epsilon yy is equal to minus mu times epsilon xx. So now how do you estimate the Poisson's ratio from a uniaxial experiment? You do the same thing, you plot the axial stress epsilon xx or the axial strain versus epsilon yy or the transverse strain. Okay, you will get some data points here. Okay. What you want is, you want a best fit straight line passing through those data points, the slope of which would be your Poisson's ratio. Okay. So similar to the expression that we got for the Young's modulus, you will find that Poisson's ratio is given by summation epsilon yy exp I into epsilon xx exp I equal to 1 to n divided by summation epsilon xx exp I squared I equal to 1 to n. Okay. That will be your expression for the Poisson's ratio. Okay. Negative slope here though, okay, because this will be in the third quadrant. Actually this is plotting negative of epsilon yy. Okay. So that is going to give you the expression for the Poisson's ratio. Okay. Now there are two ways by which you can measure the strain epsilon xx and epsilon yy. Okay. One is you can use this expression, find the elongation in the axial direction, the contraction in the lateral direction to find the strains. You can use these expressions to find the strains from overall displacement, or you can use a strain gauge and measure the axial and transverse strain. Okay. We saw what a strain gauge is in the previous lecture. So what I will do is I will stick a strain gauge here like this. This will give me epsilon xx, and I will stick a strain gauge like this to get me the strain epsilon yy, and I will stick a strain gauge perpendicular to that to get epsilon zz. Okay. So, I can directly use a strain gauge to get these strains, or I can measure it from the displacement that I see in the body. Okay. Okay. So, now we have found the expression for expression for Young's modulus and Poisson's ratio in terms of the Lamé constants. Okay. So, we have found the relationship between Poisson's ratio, Young's modulus expressed in terms of the Lamé constants. Okay. So, basically we found that the Young's modulus is given by mu times 3 lambda plus 2 mu by lambda plus mu, and Poisson's ratio is given by lambda by 2 times lambda plus mu. Okay. From here you will find that I can express lambda as, solving these two equations in terms of the Poisson's ratio, as 1 minus 2 mu 1 plus mu, and this Lamé constants would be E by 1 plus nu, 2 times 1 plus nu. Okay. So, you will get this expression for Lamé constant and Poisson's ratio solving these equations. Okay.